or I might call them the gaps, are the fact that we haven't covered the complete southern pole, and those will all get covered in the coming months. But these are the data that we actually have acquired in the first month. We have twice this amount actually during commission. We just haven't processed them all yet. But if we were to do that, then we would have twice as much resolution we have at the present time. Now, I'd like to show you this chart here. On the right-hand side, you see a black and white, what I will call image. It's actually not an image. It was developed from the previous chart, in which we take the topography and we illuminate it with sunlight, basically. It's done numerically, of course, in the computer, and it shows the image of the sunlight and darkness of the moon about a week or 10 days ago on one of our tracks. And the LROC image that you saw went through this Shackleton crater, and the image that you were seeing in great detail was part of that white area, that rim of that Shackleton crater that you can see. And at that time, they were able to see that, and of course, they didn't see the central part, which is also black to us. Now, we actually have data inside that crater, and on the left-hand side at the top, this red line shows the topography in approximately one-to-one resolution, I will call it. As you move across the crater there, it's about 20 kilometers or so, let's say 12 or 13 miles across. It's 4 kilometers deep, 2 to 3 miles deep, I suppose you can say. And it gives you an idea of the steepness of the slopes on either side, which are quite steep. And it looks very smooth in the bottom of that crater there. But actually that is deceiving, and that's one of the reasons why we have an altimeter with fairly high resolution to it, both horizontally and vertically, where the vertical resolution is essentially about 10 centimeters or maybe only 4 inches in that sort of numbering system. And the crater floor on the bottom there is just a central piece of that crater. And it's exaggerated by a factor of about 45 so that we can actually look at it. But what you see is that on the sides of the crater, it's about 30, maybe a little more degrees slope. Now that is essentially 1 in 2. So if you're driving your truck down this slope, it's very steep. I'm not saying you couldn't do it, but it is very steep. What's more, the bottom, and we believe the sides are just the same, it is also what we would call lumpy or rough. And the inner part of that chart shows the red line, which is going up and down as it goes across there. And you can see some slopes which are also at 30 or 40 degrees in various regions. But you also see the kind of the wiggles on the top of the lines there, which are what we would call immediate roughness. Now, all the spots on there are approximately 25 meters apart. So the up and down part, which amounts to the very small oscillations on the top of the tracks there, are about 5 to 10 meters in height. So over a distance of 25 or maybe 50 meters, you actually have a very large variation in the roughness or of the surface itself. And so it presents something of a difficulty if you were trying to drive over that side of sort of surface. And by the way, we went over this in just, I think it says on the chart, 2.9 seconds. This all happened. And we collected something like 200 measurements of the topography along that track. Now, the meaning of this is that if you are interested in Shackleton, and it's a great crater in many respects if you're thinking about ice, it's right at the pole. It's in complete darkness probably ever since it was formed, which I would guess is probably 1 billion or 2 billion years ago. And these slopes are sufficiently steep that you want to be extremely careful with them. And if you got down to the bottom, you're 4 kilometers below the rim, and now you have a pretty treacherous surface. It's not to say we couldn't navigate around it, but it's not nice and smooth as you would really like to have if you're going to explore that region for water ice, for example. So we believe also from what we've seen, it is typical of a number of other craters, not just in the permanently shadowed craters. But this is what Shackleton looks like, as we've seen in this first month on one track that I'm showing you here. And we have a large number through it, but I've chosen this one to demonstrate the roughness and the slopes of the surface. So back to the moderator.
Okay, thank you very much. We're now ready to take questions. If we have any in the audience today, please use the microphone and state your name and affiliation.
All right, Bob Zimmerman, Freelance. The neutron detector, the Russian instrument, showed areas where there was potential hydrogen. There appeared to be hydrogen, and it's scattered. It's not just in the permanently shadowed areas. the theory has always been that hydrogen, it's pretty hard to trap it in this place, so that the immediate response is always it's water, but we haven't known.
Right.
If it's not in the permanently shattered areas, what could be holding the hydrogen in place?
Well, if I may answer that question, hydrogen cannot exist on the surface if the surface gets warm. However, it can exist below the surface even if the surface is warm. So you may have had water deposited or some other hydrogen-bearing compound like methane or carbon or ammonia that was deposited from a comet or some other event and then was promptly buried. And so you could have this buried hydrogen that then would be lasting for a long, long period of time. It would just maybe slowly diffuse from the surface, but it would be very durable there. What we don't know is now the abundance and how deep it is buried. There may be hydrogen or hydrogen compounds on the surface that are products of the solar wind, because the protons from the sun and the solar wind are continuously striking the moon, and some of that does migrate to the polar regions. So there could be those kinds of material on the surface itself. But we need more measurements to really start to understand where it is located in detail and try to unravel the processes that deposit it there.
Just to follow up, you're suggesting the possibility that there might be hydrogen below the surface that can be mined. If so, why has that not been found anywhere in the equatorial regions of the moon during the Apollo missions? There's no evidence in the past of any of that.
Well,
why the difference?
There were small quantities of hydrogen in the up to a few hundred parts per million found in the Apollo samples, and the Lunar Prospector data showed that there is hydrogen, but not in the more abundant quantities that are expected to be in the cold regions, in the permanently shattered regions. So it's really a question of abundance. If you're talking about going there to either extract it to be as a usable resource or to try to use it for scientific reasons to understand the past history of the moon or the Earth-Moon system, it really depends on how abundant it is. And for extracting it as a resource, you need something in more of a few percent hydrogen or a few percent water would be a more significant quantity. But we need more information to be able to tell you that answer.
And of course, you're asking the same questions that the scientists are asking themselves. You know, when I said at the beginning that some of these early measurements are giving us intriguing results, this is exactly the kinds of things that we're talking about. But also, it's only the beginning. Getting more information, getting better counting statistics, and bringing to bear the best scientists and, that we have to bear on this is going to be exactly how we get to the kind of answers that we're all looking for.
Hi, Eric Hand with Nature magazine. How many days data is the LEN data based on, and how does it compare to Lunar Prospector at the 30-meter resolution that you showed? Well, I think you showed a 90 and a 30-meter picture.
Right.
30, yeah,
Yeah.
30 kilometers, sorry.
Yeah, the instrument itself is collimated such that it can be viewing around 10 kilometers at best. What was done with the images that we showed you was that we integrated the results so that we, in fact, that 90 kilometers looks similar to the kind of footprint that Lunar Prospector had. So we were trying to show you that we were getting results from LEND that are in agreement and confirmed what Lunar Prospector did.
But does the 30-kilometer data surpass?
Yes, what that's done then is instead of doing that averaging, rather the 90 kilometers is representative of what Lunar Prospector was capable of. It was not able to collimate the neutrons, in effect look down a tube, but it was looking out to the horizon. With LEND, as long as we've been operating, that 30 kilometers is what we're able to present now with the limited integration time that we've had, the amount of time over target that's necessary.